Alright, here we go. Section 1-1, rectangular coordinates. Let's get started with them. So, you've seen this before. We've got a coordinate plane. Vertical is the y-axis. Horizontal is the x-axis. In between them at 0, 0 is the origin. We call this a rectangular coordinate system, also known as the Cartesian coordinate system. See if you can figure out why. Maybe I'll ask you in class where that name comes from. That'd be a good thing to look up. But if we go in here and plot some points, we remember that we always do x first and then y. So we're going to go 6 over and 4 up, and we'll end up at the point 6, 4. All right, so let's do the same thing with -3, -5. Going left 3, down 5, into quadrant 3. All right, one more with 0, 7. Nowhere to go left or right, straight up, and we get 7. One more, -6, 0. We go to left and none up. There it is, -6, 0. Alright, so look at all this fancy things flying in here. It's amazing. Alright, quadrant 1, and we go counterclockwise. 2, 3, and 4. And we know that in, like, for example, quadrant 4, x is greater than 0, y is less than 0. And so if you know your signs of your points, you know which quadrant you're in. Okay, let's try a problem. Go ahead and pause the video and try problem 11. Alright, so this is an example of the line y equals 2x, and this is a screenshot of your graphing calculator. And so we're going to get into your graphing calculators a little bit in this video. So if you have your graphing calculators, go ahead and grab them out. We're going to take a look here. And so if you go into your graphing calculator, let me go over and grab one. There's one that you can see on the computer screen here. What you can do here is if you hit window, come back, there you are. In window here, it'll set some parameters of what you're going to see on the screen, and so that's what we're seeing here. So x min all the way down to x res, and that's for x resolution, and we'll go through what that means right here. So the scale and the y scale, actually this one doesn't have the resolution, so we'll just say on that one I'm not really going to go into it actually. We're going to leave that at 1. We never actually changed that. So it has to do with the screen performance and how clear you're seeing it. It's just the resolution. Anyway, the important stuff. X min is going to be the furthest left you can see on your screen. X max is going to be the furthest right you can see on the screen. Now this is, we see here that currently x min is -2. We want to make sure if we actually want to see -2, we should set our x min a little bit smaller than that, because the min is right on the edge. So if we want to see what's happening at -2, we're not really going to be able to do it because it's right on the border there. Alright, same thing with y min, y max, that's the bottom and the top. And then our scales, x scale and y scale, is the number of units per tick mark. So if our scale is 1, every tick mark will count as 1. But sometimes it's more convenient to change that. So for instance, 10 or 50 or 100 maybe, if we're counting big numbers. Okay. Alright, so in this example here, we can just look at our screen and tell by looking at it that our x min is -3, x max is 3, y min is -4, y max is +4, and -4, -3, oh, we're definitely not counting by 1s here. So in the y's, we're counting by 4, 2, must be counting by 2's, whereas in the x values, we're counting by -3, -2, -1, 0. We're counting by 1s here. Alright, so you don't have to have them the same in each axis. Your x scale could be different than your y scale. Alright, another example here. Let's see. Sorry, nope, same example. We're just plotting the point. What point is this? -2, +1. What quadrant are we in? We're in quadrant 2. Remember 1, 2, 3, 4. Alright, so let's find the coordinates of a point shown on a graphing utility screen. Again, this is going to be -2, +1, and assume the coordinates are integers here. So we look at it, maybe it's 2.1, maybe it's 1.9. We're going to assume it's the nice round integer of 2 and 1. Alright, with that information, go ahead and try 15 and 25. Okay, so let's dive into our first objective for this chapter, and that's using the distance formula. So we're going to find the distance, and we'll call that distance d, between these 2 points. Oh, thought there was going to be something flying on there. Nope, we'll do it ourselves. Alright, So I'm going to sketch this real quick. I'm going to scale it at 1. So 1, 2, and 5 up. There's our point 2, 5. And 4, 8, 6, 7, 8. All right, so this one here is 2, 5. And this one here is 4, 8. How are we going to find the distance between these two? What we're going to do is we're going to use a skill we learned in algebra and extended, maybe in algebra, but definitely in geometry, and that's using a right triangle. So, in a right triangle, we know that the Pythagorean formula is a squared plus b squared equals c squared, where c is the hypotenuse. So here we're going to figure out, all right, how much do we move sideways? We go from 2 to 4, so that's a distance of 2 squared. We go from 5, we go all the way up to 8, so that's a distance of 3 squared, and so that's going to be 4 plus 9, and that's 13. That's not your distance, though. Remember that that's equal to c squared. So to find our distance, we would need to square root both sides of this equation, and the distance here would be root 13. Okay? All right, so there's your formula, your distance formula. This is just a fancy way of saying the Pythagorean formula. Here's your a squared plus here's your b squared, and since that equals c squared, we need to square root it. So Pythagorean formula, distance formula, going to work the exact same way. All right, we do have a proof in here, and we can go through this. I'm actually not going to go through this too much right now. I think we'll end up doing this as part of our POW, so I'll leave that in there. You can take a look in the textbook. It's some nice steps in there. I'm going to skip through that for the time being and let you try problem 31. All right, see if you can figure out the distance on problem 31. All right, so let's do another example here. Use algebra to solve geometry problems. Consider the 3 points. A is -4, -1, B is 1, 11, and C is 1, -1. Plot each point and form the triangle. All right, let's go ahead and plot this thing first. So -4, -1. That's A. 1, 11. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 is B. And C is at 1, -1. All right, let's form the triangle ABC. The nice thing about this is it's a nice right triangle. Put that in different color there so we can see it a little bit better. Nice right triangle. All right, find the length of each side of the triangle here. So if we have our points labeled back in there, -4, -1. C was 1, -1. Let's start with this. Now these are in a straight line from each other. The y values don't change. We're going from -4 to +1. That's a distance of 5. From C up to B, which is at 1, 11, that doesn't change horizontally. It's just changing vertically. So that's from -1 to 11. That's the distance of 12. All right, so we're already ready to find out our diagonal distance because that's going to be the square root of 12 squared plus 5 squared, right? The two legs of the right triangle equal the hypotenuse, and so this turns into 13. Square root of 144 plus 25 is the square root of 169, which works out to 13. All right, so we've done B. Verify that the triangle is a right angle, okay? Actually, we kind of did that backwards here, so let me go back and do the distance formula here with A to B, and we'll do it actually piece by piece. Here's the distance formula from A to B. It would be subtract your x's, so -4 minus 1 squared, plus subtract your y's, so -1 minus 11 squared, and so this is going to be -5 squared. Don't forget your parentheses to keep the negative, plus -12 squared. And so that is indeed 13. It's the same thing, -5 squared and -12 squared. All right, lastly, let's find the area of this triangle. Remember that the area is base times height over 2. And so the base is 5. The height is 12 over 2. That's 5 times 6. Half of 12 is 6. And so that's 30. That's our area. All right, you're up. Problem 49. Give it a shot. Okay, so we've used the distance formula. Let's get the midpoint formula. We want to go halfway in between 2 points. And so another way of saying halfway is saying the average. What's the average of 2 points? So the way we do that is we add up the 2 x values and we cut them in half. We add up the 2 y values and we cut them in half. So add up your x's, add up your y's, cut them in half, and you'll have the midpoint of a segment. All right, so let's try one ourselves. Let's find the midpoint of a line segment P1 to P2. It says to plot them first, so we'll do that. A lot of times if it doesn't say to plot it, we could get away with just doing it algebraically. There's 7, so 1 comma 7, and 3, 4, 5, negative 5. 1 comma 7. Let's find the midpoint of that. And so what's halfway between 1 and 3? Well, that's half of 4, which is 2. And what's halfway between negative 5 and 7? So that's 2 over 2, which is 1. So 2 comma 1 right there is going to be our midpoint. You're up. Try problem 55. All right, objective 3, let's graph equations by hand by plotting some points. All right, so here's an example of a number of points here. So this is showing the level of risk of something versus the average annual returns, probably a stock market, something like that. And so if we have 100% foreign, 90%, oh, this is interesting. All right, so they're saying if you have 100% U.S. stock, it's going to be at about a 15.25% level of risk and about little under 14.5% in your average annual return. And so we can plot all these points here. Now, we only have points for 0 and 10 and 20 and 30. So this isn't a complete graph, but we're going to assume that the other points behave in the same manner. So we're going to have a nice smooth curve connecting our points, which is what we want to do when we graph by hand. So before we do that, we're going to learn to check to see if any of our points that were given, so in this situation 0, 4, 2, 0, if they're actually on a graph. Now we can do that without actually having to graph because we can plug it straight in. Negative 3, x, our x value here, is 0, plus our y value is 4. Does that equal 6? So negative 3 times 0 is still 0, plus 4, is that equal to 6? Definitely not, so this one is a no. How about negative 3 times 2 plus 0? That's negative 6. Is that on our line? That's not on our line either. Last chance, negative 3 times negative 1 plus 3. A negative times a negative is a positive. Is that equal to 6? Absolutely. So point C would be on the graph. So you just plug in your x and your y and check to see if the equation stays true. All right, try problem 65. Okay, so let's make some points here for y equals 2x plus 5. And we're going to make a t-table for this. So you make the t with x and y up top. All right, so you want to think to yourself, what are some really nice points to use? Try to make it as simple as possible for yourself. So for x, it's always good to have some negatives. You want to try to get 0 in there if you can for the intercept. And let's get some positives. So 2 times negative 2 is negative 4, plus 5 is 1. 2 times negative 1 is negative 2, plus 5 is 3. 2 times 0 is 0, plus 5 is 5, and now you can see the pattern. We're going to get 7, we're going to get 9. We go ahead and graph this. We have negative 2 and 1. We have negative 1 and 3. 0, and 5, 1, and 7, and 2, and 9. Now your graphs are probably going to be a little neater than this. It's kind of hard to make perfect straight lines here on the smartboard, but we can complete the graph by connecting all our points. This is going to be a nice straight line. Just a tip, anytime you see x to the first and your degree is 1, you're going to have a straight line. Okay, that's the equation for a line. X to the first power equals y. If we take a look at another one, y equals x cubed. So now, when we do our x's and our y's, negative 2 cubed is negative 8. Negative 1 cubed is negative 1. 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. Now when we graph, we get something slightly different. Negative 2, negative 8. I think that's 8. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1 and 1. 0, 0, 1 and 1. 2, 3, 4, 5, 6, 7, 8, and 2. If we connect these in a nice graph, notice how it looks like it needs to kind of bend right in there, and it does. So that's what an x cubed graph looks like, going up and down forever there at the ends. Okay. Oops, let's try not drawing the arrow. There we go. All right, so we'll take a look at one more here. Oh, that's it. So none for you to try, but just an example of how to plot points by hand. Okay, so now something we're going to use again and again and again and again and again and again and again using our graphing calculator. So to do that, on our graphing calculator, we have y equals, and that's where your go-to for graphing lines and curves and all that good stuff. So you'll notice here, clear that out, y1 equals, y2 equals, y3 equals. It's always y by itself. So that's what this chart in our book and in the video here are saying. If we have an equation, we need to rewrite this so that we have y by itself. All right. So on this one, it's pretty easy. Y by itself on the right, that's the same thing as y by itself on the left, just flip sides. Sometimes, though, we do need to rearrange so that we can get y all by itself, and just doing some algebra to do that. So we can take a look at an example here. Let's rewrite this so that y is by itself. We would minus 3 first, negative 2x plus 5y equals negative 4. We would add 2x and have 5y equals 2x minus 4. And then we divide by 5. Y equals 2x minus 4 over 5. All right, and that we can put into our graphing calculator and let it do the graphing work for us. So we can follow our steps here to get 2x squared plus y equals 12. So solve for the equation for y in terms of x. We've got to do that first. So we're just going to move it over. Y equals negative 2x squared plus 12. All right, step 1, check. Step 2, enter the equation to be graphed into your graphing utility. Now the textbook says graphing utility because you can graph on a computer or other software things, but graphing utility just means your calculator. So negative, not negative over here, that's a minus. Negative 2x squared, oops, where's my x? There it is, x squared plus 12. All right, I've entered it in. Step 3, choose an initial viewing window. Without any knowledge, it is common to choose the standard viewing window here, negative 10 to 10, negative 10 to 10. So let's go back and make sure our window is looking good. Hey, look at that. That's the standard one. Most times your calculator will be in this, unless, of course, you change it, and then it'll be in whatever you've got last, whatever you did last. All right, step 4 is graph the equation. So we go over here, graph, and we hit that button. And here comes our graph. All right. So x squared is going to be a parabola. It's opening downward, so we've got that. We need to adjust our viewing window until a complete graph is obtained. Notice the top here isn't in there. So now we go to our zoom here, all right? And if we go to the ones we use the most, ZBox, we'll come back to that. The other one we use a lot is Zoom Fit down here. If we do Zoom Fit, it's going to adjust it so our height works out. Now this is probably more than we need, but it will give us the top. We can go back to the window. Look how Y max is 12. Y min, we don't really need to go all the way down like that, What if we change this a little bit below? How about negative 20? And how about positive 15? So we know we're above and below. And there's a nice graph there. We could change our y scale as well if we wanted to maybe count by 2's. Make your tick marks a little more reasonable here on your y-axis. All right, so your job is to graph 83. See if you can do it. Okay, so we're going to use a graphing utility to also create tables. So create a table that displays the points on the graph of 2x squared plus y equals 12. Same one we did before for these values. All right, solve the equation for y in terms of x. We already did that. We've got our y equals. Enter the expression in x following the y equals prompt of the graphing utility. Okay, so we've already done that. It's already in there. Let's set up our table. So, table right here, we're going to hit second graph. It's the one above graph, second graph. Give us our table. All right, but we don't really want these values. We want these values over here. All right, so how are we going to get to those? It's table set that we want. Just how window sets the parameters for our graphing, table set sets the parameters for our table. So we'll go into table set, second window, table set. What do we want to start with? We want to start with negative 3. What do we want to count by? That's what this is, delta table, right? Change is going to be 1. So we'll do 1. And now we're going to use auto here. We can change this to ask if we want to independently put numbers in ourselves. So if we do auto and we go to table, bada boom, bada bang, there we go, negative 3 all the way up to 3. There's your y values. Now quickly, let me go back and change that independent to ask. And now if we grab, it's waiting for our value. And we can type in whatever we want. Negative 2 tells us the answer is 4. All right, so we can have our solver going on this one. All right, so lastly here, I believe this is the last objective. Find the intercepts from a graph. X-intercepts are where the graph crosses the x-axis, and y-intercepts are where it crosses the y-axis. All right, so find the intercepts from a graph. All right, so here, just looking at it, what are the x-intercepts? Negative 3, 3 halves, and 4 1/2. What are the y-intercepts? We have 3. We have negative 4/3, and we have negative 3 1/2. So you're just going to grab the y values for the y-intercepts and the x values for the x-intercepts. So try problem 71. Okay, let's use the graphing utility to approximate those intercepts. So same equation. We're going to put it in there, and now we want to find the intercepts. So here's how we're going to do it. We know, first of all, from graphing this, that it crosses like this. So just visually, we know that there are 2 x-intercepts, and we know that there's 1 y-intercept. All right, so the y-intercept, we can go into our table, and we could, if we go in here and we make x 0, because if we go back to our graph, isn't the y-intercept where x is 0? So let's go back to our table, and we'll make x 0, and see what happens. So the y-intercept is 12. Now what about the y-intercept, or the x-intercepts? When is y going to be 0? All right. So let's go ahead and use a, where is it? Hold on one second. I believe it's in format. Nope. Calc. There it is. We're going to calculate. That makes sense. We want the zeros. The x-intercepts are going to be the zeros. All right. So what this does is it brings you back to your graph, and it asks you first for the left bound. So that means go a little bit to the left of where you think the 0 is. So I'm going to move my cursor. A little bit to the left, doesn't need to be precise, and hit enter. Right bound, we need to go a little bit to the right and hit enter. And then guess, as close as we can to where we think the intercept is. Here we go, intercept negative 2.449, and we can do that the same thing going on the other side. So we'll start over. Let's calculate our 0. We need a left bound. We need a right bound. And we need a guess. And positive 2.449. All right, so those are our intercepts. Use that knowledge. Use your calculators. Try problem 93. All right, that's it. Any questions, we'll be sure to go over them in class, and good luck on all those problems.